So let's now systematically analyze the types of bifurcations that can exist in one dimension. The first example is what's known as a saddle node bifurcation. The generic example that illustrates this is the equation of motion x dot is equal to r plus x squared. Our control parameter here is r, and we'll see that as r is varied, we can start when r is positive, there are no fixed points, and then as r passes through 0, 2 fixed points are born from the vacuum. So let's illustrate what happens to the flow when I vary r. And so let me draw then 3 plots showing x dot as a function of x. For the 3 cases, r is positive, r equals 0, and r less than 0. So for r positive, this is the function x dot equals r plus x squared is a right side up parabola that doesn't cross the x-axis. So it looks something like this, for example. So the flow is always to the right. There are no fixed points. When r is equal to 0, then the function x dot equals x squared just kisses the x-axis at 0 with 0 slope. And so we have this marginal point where from the left we're attracted very slowly with time, and to the right we're repelled also very slowly with time. But finally, if r is negative, then the parabola falls below the x-axis, and what we're going to have is a stable fixed point for negative values of x and an unstable fixed point at a positive value of x. And we can see just by inspection that the fixed point values are equal to square root of r and minus square root of r. To the left of the unstable fixed point, we have flow towards the stable fixed point, and to the right of the unstable fixed point, we have flow away from the fixed point. And we can summarize what we've seen here by something known as the bifurcation diagram, which is basically a plot of the fixed points as a function of the control parameter in the system, which in this case is r. So let's plot the fixed point values x star as a function of the control parameter r. So first point is that for r positive, the flow is always to the right. The flow is always to increasing r. So we can represent the flow here as always going to larger values of x. And it's faster and faster the further away you are for larger r. And as you get closer to r equals 0, the flow is slowing down. So on the other hand, if r is negative, then we have 2 fixed points, one stable and one unstable, one at square root r and one at minus square root of r. And so let me represent them in this bifurcation diagram. There is a stable fixed point at minus square root of r and an unstable fixed point at plus root r. So let me draw the unstable fixed point as a dotted line, the stable fixed point as a solid line. So this is at minus square root of r. This is at square root of r. And let's fill in the flow pattern that goes with this. So once again, for r negative, we are flowing towards a stable fixed point. So the direction of the flow is reversed inside of the parabola. And so we have flow like this. Outside the parabola, the flow is still always upward. And so we are drawn towards the stable branch of the fixed point and we're repelled away from the unstable branch of the fixed point. To just summarize here, we have this is the stable fixed point and this is the unstable. And why it's called a saddle node bifurcation is that you see that the parabola is like the shape of a saddle, and when the saddle passes through the x-axis, a bifurcation has occurred.